Hello everyone. Today I'm going to help you with the topic units and measurements. So in NCERT textbook, if you consider the order of topics, first of all you have physical world, which gives you an idea about what physics is, what are we going to learn in this course, in your higher secondary course, what you are going to learn. It gives a basic introduction about how you are going to learn science, what are the different types of forces, which are the fundamental forces, and all these kinds of basic introduction is given in this topic in physical world. Okay. In units and measurements, what we are going to study about is a prerequisite of learning science, not just physics, science. So first of all, what is meant by physics? Okay, so there is a large number of a multitude of definitions for physics. So generally, in the most simple way, we can say physics is the study about nature and its laws. So in physics, what we do is we observe the nature. We observe what we see around in our surroundings, and we try to understand them. How do we understand them? For example, we can, in physics or in our surroundings, we can see a multitude of physical phenomena. Like we can see an apple falling down, we can see the rain, we can see wind, we can experience wind, we can observe thunderstorms, we can observe lightning. So these are all different kinds of physical phenomena that we can observe in our surroundings. What we do in physics is we are trying to make sense of what laws are causing, or what laws decide, or what laws affect these phenomena. Like for example, an apple is falling down. Okay, so since the beginning of time, or at least since the beginning of observations by human beings, we've been fascinated by why all objects are falling downward. It was not Newton who asked the question, why is everything falling down? Why is it not going up? Okay, Newton formulated the laws and theories behind that. That is another question. So everyone, almost anyone who can think, must have asked that question to themselves. Why does everything fall down? Now we know the answer to that question. Okay. Now the other thing is, I've mentioned about lightning. Okay. Human beings were always fascinated or terrified by lightning. Okay. So there is a question: what causes lightning? How can we explain lightning? Now we can explain lightning. So nowadays physics is, or science has developed beyond our imagination. Now what we are going to do in this topic is how to begin with that. In this topic, we are going to see how to begin with physics, how to begin with science. Okay, this is, like we said, like we discussed, it is a prerequisite for learning science. So in this topic, we are going to see how measurements are made. Okay, how do we observe things, how do we make measurements? Okay, so here we are going to begin with the topic now. So what are the topics that we are going to discuss in this? So here we'll be learning about physical quantities. Okay, we'll learn about physical quantities. We'll learn about units. We'll learn about how to take measurements and how to deal with errors. We'll deal with error analysis in this. We'll look at dimensional analysis. Okay, and we'll discuss about some basic measuring instruments. So you may not be familiar with all these terms, you may be familiar with one or two. So we are going to discuss in detail about them. So first of all, let's discuss what is a physical quantity. Okay. So these two terms, physical and quantity, they not be so alien to you. You may be familiar with them, but here we have a specific meaning for physical quantity. Okay. So what is a physical quantity? Suppose I take an object. I'm taking this board. Okay. This board has some dimensions, some measurements. You can say there is length and breadth. I'll say that this length and breadth, these are physical quantities. Okay. Then another thing is that I'm taking this phone. It will have similar dimensions like length and breadth. It will have some weight. So these quantities like their length, breadth, mass, weight, these quantities are what we call as physical quantities. Still, I didn't say how can we define physical quantities. Suppose, let's consider something. Length, like I've mentioned, length is a quantity. Mass, okay. Then time, and I'm mentioning about another thing, beauty. Okay, what is the difference between these three and beauty? So from these list of things, it will be easy for you to identify the odd one. It is beauty. What does it mean by that? Because here I'll say that beauty is the old one, because I can measure length, mass and time without any confusion. Okay, but beauty cannot be measured simply like that. If I have two observers A and B, let's consider two observers A and B. Okay, and I have a flower here. You'll have to deal with this flower. Okay, anyway, suppose these two observers A and B, they have similar measuring instruments, and they are going to measure the length and breadth of this board. Okay, once again, A and B are going to separately measure the length and breadth of this board using the same measuring instrument. Now, we know that if they are going to use same measuring instrument, same measuring techniques, proper measuring techniques, then they'll get the length and breadth of this board. Both of them will get the same values. Or suppose they are going to measure the weight of an object. Suppose they are going to weigh my weight. Okay, I'm going to stand on a weighing machine and I'm going to allow them to record my weight. Both of them will record the same weight. But suppose they are going to look at this flower. Okay, and I'm asking them to rate. Suppose I'm asking A and B to rate the beauty of this flower on a scale of 1 to 10. That is what we generally do. So A may find this flower beautiful depending on his senses, his aesthetic sense, which is going to be different from B. Okay, B may also find this flower beautiful, but the level that they, or the rating that they provide, it will be different. It will be according to the observer. Beauty lies in the eyes of the beholder. Now, so we can say length, mass and time can be measured unambiguously. That means there is no confusion between different observers while measuring length, mass, time or current or anything. But beauty is not easily measurable. Okay, because that is how we define physical quantity. Physical quantity is something that can be measured clearly. It can be measured unambiguously. There should be no confusion in measurement. That's it. So we can say length, mass, time, these are physical quantity. Velocity is a physical quantity. Acceleration is a physical quantity. Force is a physical quantity. Pressure, energy, work done. All these quantities are physical quantities because they can be clearly measured. So we can clearly now we can have an idea about what physical quantity is and what is not a physical quantity. Okay. So in physics, there are a large number of physical quantities. Like we said, length, mass, time, temperature. Then we have current, charge, potential difference, energy, torque, pressure, a large number of physical quantities, which you are going to study in this span of 2 years. Here in this topic, you'll be coming across many of these physical quantities about which you're not that clear. Because, for example, you're going to be coming across a physical quantity called permeability, permittivity, about which in detail you're going to study only in 12th standard. Okay, so we were discussing about physical quantities. So physical quantity is any quantity that can be measured unambiguously by any observer, and various physical happenings can be explained in terms of these physical quantities. They can be explained using these physical quantities. Example, what I have already said: mass, length, time, speed, velocity, force, etc. So there are a large number of physical quantities about which we are going to study. So here we are going to see a classification in physical quantities. So we are going to classify, generally we are going to classify physical quantities. There are a large number of classifications. We can classify physical quantities into scalars and vectors. We are not discussing about that classification. We are going to classify physical quantities into fundamental quantities and derived quantity. Okay, fundamental and derived quantity. So what is meant by this? This term is clear for you, fundamental or base. Okay, let's take an example. I want you to consider a building. Okay, I want you to consider a building which is made of a large number of blocks, large number of building blocks or bricks, I can say, large number of bricks. Now, these bricks are what we call as the fundamental building blocks of that full building. Like that, we have certain physical quantities which are independent of anything else. Okay, they are not depending on anything else. For example, length. Length is a fundamental physical quantity that doesn't depend on any other quantity. We don't need any other quantity to define length. We don't need the help of any other quantity to define length. Another one is mass. Okay, mass is another fundamental quantity. We don't need anything else to define that, any other quantity to define that. Then we have time. Time is another fundamental quantity. So all these which can stand independently, which do not need any other quantities to explain them or to support them, they are independent. Such quantities are what we call as fundamental quantities. There are other fundamental quantities as well, but we generally take length, mass and time for our example. There are other fundamental quantities as well, like temperature, current, luminous intensity. These are all fundamental quantities. They will have some certain units. About units we'll discuss a little later. And then what is derived quantity? Okay, again that is clear from the name. Suppose we have a quantity called speed. I hope you're all familiar with the term speed. That is one of the most simplest quantities that we come across. Speed. What is speed? We can simply say speed is the rate at which a body is changing its position, or we can simply say it is the distance traveled divided by time. So we can say speed can be written as length divided by time. Okay, speed is length divided by time. So here we make use of two different fundamental quantities to define speed. Is that clear? We need two different quantities, two different fundamental quantities, length and the time, to define speed. So we can say speed is depending on length as well as time. It cannot be called as a fundamental quantity. So that is why it's a derived quantity. Now, what is then acceleration? Another quantity is acceleration. So acceleration, a fundamental quantity? No. We know that acceleration is the rate of change of speed. That means change in speed by time. Change in speed divided by time. Again, two different quantities. This is not even a fundamental quantity. So this one is a derived quantity. Then we have another quantity called maybe force. So you have you know the famous relation, force is equal to mass into acceleration, Newton's second law of motion. Now this force is again a derived quantity. How can we make sure that this is a derived quantity? Because we have mass and acceleration. Mass is a fundamental quantity, acceleration is another derived quantity. So it doesn't matter which quantities are multiplied to get force, it is a derived quantity. Okay. So we have a number of fundamental quantities. Actually, we accept 7 quantities as fundamental quantities, 7 different quantities as fundamental quantities. We'll discuss about it. We'll name them when we are dealing with units. And we have all the other quantities come up in this category, that is derived quantity. So in addition to fundamental and derived quantities, we use another classification, that is supplementary quantity. Okay. So these supplementary quantities, actually we cannot include them in fundamental quantities or derived quantities. They are actually in between. So generally what we use or what we categorize as supplementary quantity, those are plane angle and solid angle. I'm just mentioning these quantities. The definition of this quantity, what we mean by this plane angle and solid angle, it will be discussed in detail when we are discussing about supplementary units, when we are discussing about units. Now, we have now a basic idea about what physical quantity is, what is fundamental quantity, what is derived quantity and all. Now, we need to step into the next section. We cannot consider it as next section. I'm just mentioning it as next section. It is unit. Okay. So the term unit is not at all alien to you. You are all familiar with the concept of units. You've been using the term units for a long time now. Anyone? Now suppose you are mentioning your own height. Okay. Suppose your height is 180 centimeters. That is about 6 feet. Now, 180 centimeters. Isn't it enough to say it is 180? Or I am saying that the mass of a particular object, mass of my bag, it is, including the things in it, it is 10. Is it clear? I'm just mentioning that the mass is 10. It is not clear. No. Suppose another thing. Suppose we are going to compare the mass of two objects. We are going to compare the mass of this object and this object, this phone and this pen. Okay, I can feel the difference in their masses. Okay, it's fine. I can say that this is slightly heavier than this. Okay. So similarly, we can compare the mass using different things by feeling it with our hand. Suppose I'm taking maybe a dumbbell and a coconut. Okay, I'm taking a 10 kilogram dumbbell and a coconut. We can see the difference in the weights in our hand. I can say that the dumbbell is much heavier than the coconut. So many times we can compare the mass of these objects by feeling it in our hands. Suppose we have a bus and a car. Okay, we have a large bus and a car. Can we compare their weights by feeling it in our hands? Unless we're not Superman, Unless we are Superman, we cannot do that. Okay, so we cannot compare the weight of every object by feeling it in our hands. Okay, leave it the case of masses. Let's consider the size of an object. I can say the size of this phone is definitely smaller than this board. The area of this phone is definitely smaller than this board. Okay, fine. We can say that we can compare the size of many objects that are visible to us like that. Suppose I want to compare the size of a bacteria and a virus. I want to compare the size of a bacteria and virus. As far as we are concerned, bacteria and virus both are very small. We cannot see them with our naked eyes. But are they of same size? No, bacteria, the size of bacteria is much larger than a virus. So how do we do that? Or suppose we consider two celestial objects. We consider the sun and the moon. Sun and the moon, they appear to be of same size to us. Okay, we can just include the size of the sun, the angular position of the sun can be included within these 2 fingers. I'll say that, okay, I can see the sun within these 2 fingers. We are not supposed to look directly at the sun anyway. And I can also include the size of the moon also in between these little fingers. So sun and moon, they basically appear of same size to us. But we now know that they are actually not of same size, not even close. Sun is much bigger than the moon. Then why do we feel so? Why do we feel that they are of same size? Because the sun is very far away compared to the moon. The moon is at a distance of about 3 lakh kilometers and the sun is at a distance of about 150 million kilometers. That is about 15 crore kilometers. That is what we call as astronomical unit. So anyway, so we cannot simply compare two objects without the help of a standard. That is what I was going to say. We cannot compare two physical quantities without a standard. Okay, I can say that I am taller than him or I am shorter than her, but to clearly define these length, mass and all, we need some certain standards, and these standards are what we call as units. Okay, I can say that I have walked 10 steps. Okay, so this distance between here and the door is 10 steps, I can say that. So someone else comes and does the same. Maybe he has longer legs and it takes only 8 steps to reach the door. So there is a confusion in this. So we need an internationally accepted standard to measure physical quantity. Okay, once again, we need an internationally accepted standard to measure a physical quantity. Such a standard is what we call as unit. Yes. I say that my height is 180 centimeters. Say my height is 180 centimeters. Here there is no confusion because this word centimeter, it is universally accepted. Or I say that the mass of an object is 10 kilogram. It is universal. There is no confusion. If I say it is 10 kilogram, it is 10 kilogram. Here it is 10 kilogram, maybe 10 kilometers apart. Or if I take it to another position on earth and measure it, it is going to be same 10 kilogram. So a unit is it's an internationally accepted reference that we can use to measure physical quantity. Suppose any physical quantity, like we have seen length, mass or anything. A physical quantity can be represented like this. Quantity is equal to a numerical value, a number, into a unit. Okay, a physical quantity is generally represented as a number, a numerical value into unit. For example, we'll say that the length or height is 180 centimeter, mass is 10 kilogram, the duration of this class, the time, it is 1 hour. Okay, we represent physical quantities like this. Here, we can say this 180, that is the number, and centimeter is a unit. Here 10 is the number, kilogram is the unit. Here 1 is the number and hour is the unit. So like this we can represent any physical quantities in terms of a number and a unit. Maybe sometimes we'll use different units, like for example, Suppose someone wants to measure my height in meters. Someone wants my height in meters. Then I can say 180 centimeter. How can we convert it into meters? You are familiar with that. It is 1.8 meters. Okay, 180 centimeter. It can be mentioned as 1.8 or 1.80 meters. These zeros are all significant. We'll see about that. Now this 180 centimeter or 1.80 meters. Here the quantities, the numerical values are different, right? Yes. And the units are also different, centimeters, meters. There is a difference in numerical value, there is a difference in units. So when we represent a physical quantity by a numerical value and unit, and I am going to convert it into another unit. Suppose one is N1 U1. Okay, N1 U1. I am going to convert it into another unit. N2 U2. Okay. What is the significance of this sign? Because even though I am going to convert the units, I am not going to change the physical quantity, because whether it is 180 centimeter or 1.80 meters, both are meaning the same thing. My height is 180 centimeter. So when we change the units, the physical quantity will not change. So that is one important principle that we are going to use throughout our life, conversion of units. Okay, we are going to convert units into one another throughout our lives, throughout our education now. When we convert units, the number will change, that is numerical value will change, units will change, but the quantity will not change. Whether it is 180 centimeters or 1.8 meters, both are meaning one and the same. Now, if we consider this 1 hour, okay, 1 hour, let's take another example, 1 hour. Suppose someone wants to represent that in seconds. Okay, how many seconds are there in 1 hour? It's 3600 seconds. Okay, here the numerical value has changed, the unit has changed, but is there any difference in the physical quantity? Whether it is 1 hour or 3600 second, both are meaning one and the same. So you'll have to keep this in mind. We can convert a physical quantity from one unit to another. While converting the physical quantity from one unit to another, the number will change, the units will change, whereas the actual value of the quantity remains the same. Okay, that is one useful principle that we'll have to keep in our mind. Now, we have seen that physical quantities can be classified into fundamental as well as derived quantities depending on whether a quantity needs the help of other quantities to be defined. Okay. So depending on that classification, fundamental and derived quantities, depending on that classification, we can classify units also into fundamental as well as derived quantities. We can classify units into fundamental and derived units. Sorry. Now, how do we do that? How do we classify? Let's see. Suppose I'm classifying them into fundamental and derived units. What is meant by fundamental or base unit? Simply it is the unit of fundamental quantity, that's all. Okay. Suppose if we have a fundamental quantity, the unit of that fundamental quantity is what we call as fundamental unit, because a fundamental quantity doesn't require any other quantity to define it. Just like that, the fundamental unit also doesn't need the help of any other unit. Okay, they stand independently. For example, the quantities that we classify as fundamental quantities, they are length, mass, time, temperature, and we have current, electric current, we have amount of substance, and we have luminous intensity. So we have 7 fundamental quantities generally. We define these as this is the internationally accepted list of fundamental quantities. Now the units of these quantities are what we call as fundamental units. It's as simple as that. For example, the unit of length that we are familiar with, it is meter. So that's a fundamental unit. Its symbol is m, small letter m. Then the unit of mass, you're all familiar with the unit of mass, it is kilogram. There are other units to mass like gram or milligram, or there are other units to length like centimeters or kilometers. And why we have specifically used this meter and kilogram, we'll discuss about that a little later. So the symbol of this kilogram is familiar, it's kg. We have the unit of time. What is the unit of time that we are going to use? Seconds, yes. There are other units as well. We'll discuss what the speciality of these units are later. Temperature, what is the unit of temperature? There is degree Celsius, there is Fahrenheit, there is Kelvin, and the one that we are going to write here, it is Kelvin. Again, why we are using Kelvin instead of Fahrenheit and Celsius, we'll discuss about that. So Kelvin, it is named after Lord Kelvin. Its symbol is K. Now we have electric current. Electric current is considered as a fundamental quantity. It is accepted as a fundamental quantity. And its unit is ampere. And its symbol is A. Then we have amount of substance. And the unit is mole. And the symbol is mole itself. So mole is actually a number. Clearly, it's a number. It's a certain number corresponding to amount of substance. For example, we are familiar with the 1 mole of atom means 6.023 into 10 to the power 23 atoms. Or anything. For example, if you are considering 1 mole of people, it means 6.023 into 10 raised to 23 persons. 1 mole of rice grains, it is 6.023 into 10 raised to 23 rice grains. Anyway, then there is luminous intensity. It's an amount of brightness of a light source. Simply, in the most simple terms, we can say luminous intensity is an amount of brightness of a light source. Okay, and its unit is candela. Symbol is CD. So these are the fundamental quantities and their respective units. Okay, so you'll have to know these fundamental quantities, fundamental units. Actually, this fundamental units, meter, kilogram, second, Kelvin, ampere, mole, candela, these all have clear-cut definitions. Okay, but these definitions you don't have to learn them by heart. It is given in your NCERT textbook for your information, but you don't have to learn these definitions by heart. Okay, actually, meter is defined in terms of the speed of light, because speed of light is the absolute constant that we know about, speed of light in vacuum. The meter is defined, meter is defined as the distance traveled by light in a particular amount of time. The time is very small. Okay, the time is based on the measurement using an atomic clock. So you don't have to clearly learn these definitions and all by heart. Okay, you just have to know that there are certain definitions, that's all. Now, these are fundamental quantities, fundamental units. That means the units corresponding to fundamental quantities. We are going to come across these quantities again and again while we are learning this topic. Okay, now we have another type of units known as supplementary units. Supplementary units. That means they cannot be classified either into fundamental units or derived units. Why is that so? There are only 2 supplementary units that we are going to learn here. One is the unit for plane angle, or simply angle. Unit for plane angle, or the angle that you know about. Okay, that is what we call as the unit of angle. You have learned, you are familiar with angle and its measurement, and the unit of angle that you use now, it would be degrees, like 90 degrees, 360 degrees, 180 degrees. But the unit of angle that we are going to study about is radians. This is the unit. Actually, the unit of angle, plane angle, it is radians. It can be converted into degrees, about which you will study. Now, what is meant by this radian? Let's consider an angle. Suppose we have a ray over here and another one. Okay, so we can consider two line segments which are intersecting. This thing over here, that is the angle. That is what we call as plane angle, because everything, these two lines and the angle, it comes inside the plane of this board. This is what we call as the plane angle. We generally represent it by theta. So let's see how to define that angle, because I'm explaining it in detail because you will need that concept. You will need that concept of radians. Suppose we consider an arc. You are all familiar with arc. You all know that what an arc is. Suppose this is an arc of a circle. This is an arc length. This is the radius and this is the angle. Okay, you know that if this angle is 360 degrees, then that means it is a full circle. We are not discussing about that. We know that as the angle increases, okay, as the angle increases like this, suppose this is the radius, these are the two arms. Suppose as this angle increases, you can see that the arc length also increases. Once again, the radius is fixed. When I increase the angle, the arc length also increases. So you can see that this arc length is directly proportional to the angle. As we increase the angle, the arc length also increases. Now, angle is defined as, plane angle is defined as the ratio of arc length to radius. Ratio of arc length to radius, and that's it. Okay, so what is radian? We can say radian is the unit of angle. And what is angle? It is the ratio of arc length to radius. Is that clear? So if we have a larger arc length, we'll have a larger angle. Clear? And if we have a larger radius, that means we'll have a smaller angle. Let me show you something. Suppose I'm taking this same arc length. Okay, it is almost same. Now I'm using much larger radius. Okay, so we have same arc length but much larger radius. So the angle will be much smaller. You can see that this angle is smaller than this. Okay, so it is clear. What is radian? Radian is the unit of angle which is defined as length divided by radius. Suppose we have an arc of length 1 meter. Okay, suppose we have an arc of length 1 meter and an arc length of 1 meter. So here R is 1, L is also 1. So we have an arc whose radius is 1 meter, arc length is 1 meter. Then this angle, this is what we call as 1 radian. How does it come? 1 meter divided by 1 meter. That is what we call as 1 radian. So you must have sensed some problem in this, because theta is equal to length by r in radians. Okay, so here theta is equal to L by r, and if what is the unit of length? It is meter. Unit of r, that is also meter. Then what is the unit of L by r? It should be unitless. It should not have any units. Yeah, that's the problem. That is why we classify it as supplementary unit. We do not include it in fundamental or derived unit. We just classify it into something else. We just classify it into a new classification, a new category. That is supplementary unit. So You can say clearly this radian or the plane angle, it is actually a quantity without any units, but we define another quantity. So that we need this unit because we are going to deal with this angle, plane angle, in a number of applications. So you'll have to be familiar with this thing. The angle is defined as the ratio of arc length to radius. Angle is defined as the ratio of arc length to radius. Larger the arc length, larger will be the angle. The other way is also true. Larger the angle, larger will be the arc length. Is that clear? Okay. Now suppose we consider a full circle. Okay, full circle. What is the arc length of a full circle? It is not an arc, it's a complete circle anyway. What is the arc length of a full circle? It is 2 pi r. So if radius is r, what is the angle corresponding to full circle? What is the angle corresponding to full circle? It is arc length is 2 pi r divided by r. Okay, angle corresponding to full circle, it is 2 pi r divided by r, and it comes to 2 pi. So 2 pi radian, 2 pi radians. So if we are representing in radians, what is the angle corresponding to a full circle? It is 2 pi radians. And that is what we call as 360 degrees. So we can have a conversion factor. 2 pi radians is equal to 360 degrees. Yes. 2 pi radians is equal to 360 degrees. Then what is 1 radian? 1 radian is 180 divided by pi. So you can have conversion factor 180 divided by pi degrees. So you can have conversion factor between radian and the degrees. So once again, we have radian as the unit of plane angle. That is the angle that we are generally seeing in our calculations and all. It is plane angle, it is the angle between two line segments, and that depends on the arc length as well as radius. It is defined as L by R. Okay, theta is equal to L by R radians. And what is when is the angle 1 radian? Angle is 1 radian when we have an arc whose arc length is equal to the radius. If we have arc length equal to the radius, then we'll say that the arc length is the angle is 1 radian, and the angle corresponding to a full circle is 2 pi radians. Then angle corresponding to a semicircle is it is pi radian, that is 180 degree is pi radian. The angle corresponding to a quarter circle, that is a 90 degree angle, it is pi by 2. You can just note it over here. 2 pi radians, it is 360 degrees. Pi radians, it is 180 degrees. Pi by 2 radians, it is 90 degrees. So similarly, so in mathematics you will learn trigonometry, and in trigonometry it is basically the study about angles and all, and in that you will be using this radians now onwards. So you will see that in mathematics classes. Now the second supplementary unit that we are going to discuss is solid angle. So you were all familiar with the term plane angle, only the term radian was new to you. Now this term solid angle, I think that for most of you this solid angle may be a new term. We'll first discuss what the solid angle means, and we'll discuss about its units. Its unit is radian. Now suppose we have a cone. Okay, I want you to imagine a cone. Okay, we'll see whether we can get a cone or something. Suppose we take this sheet of paper and we make a cone out of it. So you'll have to adjust with my cone. Okay, so this is a cone. Plane angle was the angle between two line segments, whereas by solid angle what we mean is this region over here. Okay, So the larger this angle, larger the solid angle will be. So what we mean by solid angle is this concept over here. I'll try to represent that by a diagram. Suppose we have a surface like this, a spherical surface. You are all familiar with spherical surface. Suppose this is a spherical surface. This is a curved spherical surface. That's a part of a sphere, like spherical mirrors that we use. Now, let's consider the radius of this sphere. Okay, so I hope the diagram is clear. Now, this is a spherical surface and these are the radii. Radii, it can be an imaginary radii. You don't need to have any physical thing present over there. Now, by solid angle, what we mean is this portion. Okay, or we consider a cone like this. This is solid angle. Okay, so again, now you have an idea about how to visualize the solid angle. We can say solid angle is the 3D version, three-dimensional version of plane angle. Plane angle is familiar to you, it is easier to visualize. Now, I want you to take real effort in visualizing a solid angle as well. Okay. Now, how do we define solid angle? We use the symbol omega to represent solid angle. Okay. We use the symbol omega to represent solid angle. Solid angle depends on this area. Suppose this area, spherical area is A. And this radius is R. Okay, spherical area is A and the radius is R. Then solid angle is defined as, how did we define plane angle? It was arc length by radius. Here we do not have an arc length, we have an area. Solid angle is defined as the ratio of area to the square of radius of the sphere. Okay, ratio of area to square of radius of the sphere, and that unit is what we call as steradian. So now again there is that problem, because what is the unit of area? It is meter square. What is the unit of r square? Again, that is meter square. So meter square by meter square, it should be unitless. Okay, so just like plane angle, solid angle is also, it cannot be represented in terms of the fundamental quantities, fundamental units. Yes, because there is no meter here, meter gets cancelled, but we need a unit, so that is why we gave the unit steradian. So steradian is actually a measure of how large the solid angle is. I will have to keep one more thing in mind. What is the solid angle if it is a full sphere? So like in plane angle, we have seen what is the plane angle corresponding to a full circle. It was 2 pi. How did we get that? The total arc length of the circle divided by r. Here, to get the plane angle associated with a sphere, plane angle associated with a sphere, if we consider a full sphere like this, okay, what is the angle, solid angle corresponding to a full sphere? It is total area of the sphere divided by square of the radius. What is the total surface area of the sphere? You are all familiar with that formula. It is 4 pi r square divided by r square. So r square will get cancelled, will get 4 pi steradian. So the total solid angle associated with a full sphere, it is 4 pi steradian. Just like what we have mentioned in the case of plane angle, the plane angle associated with the circle, it is 2 pi radians, and the solid angle associated with a sphere is 4 pi steradians. Okay. Now, so these two quantities, plane angle and solid angle, and their units, radians and steradians, you will have to be familiar with that. Now we'll look at derived quantities. So we have seen fundamental units, supplementary units. Now we'll look at derived units. So what is derived units? Again, the definition is almost redundant. The definition of derived unit is simply the unit corresponding to derived quantities are what we call as derived units. For example, we have the unit, I'm mentioning meter per second, sorry. Is it a fundamental unit? No, there are two different units in that, meter and second. Is it a supplementary unit? No, this is what we call as derived unit, because here we have mass raised to a power of 1 and second raised to a power of -1. So here we have two units combined in some way to get another unit, that is what we call as the derived unit. Now we'll discuss about other derived units as well. What is the unit of acceleration? Yes, that is it. Meter per second square. Is it a fundamental unit? No, there are two different units, mass and again second. You can see that in both these cases, in the unit of speed as well as acceleration, we have the same fundamental units, meter second, but the way they have combined is different. So depending on that, we can have different quantities as well. And then I'm going to mention another unit, kilogram meter per second. Which quantity does this unit represent? It represents momentum. Okay. Again, here we have units of mass, units of length, and unit of time. Again, derived units. We have combined fundamental units to get a derived unit. Now, we'll say, okay, maybe force. What is the unit of force? Suppose you're telling to me that this unit of force is Newton, it is independent. Yes. Is it independent though? Is it independent? This Newton, okay, I don't see any other fundamental quantities. Can you see? No. But we can say, even though this unit Newton, it looks single, that is, we don't have any other quantity associated with that, it is not quite fundamental, because what is force? Again, we come across this famous equation, F is equal to ma. If force is the product of mass and acceleration according to Newton's second law of motion. Now, what is the unit of mass? Kilogram. What is the units of acceleration? We have it over here, meter per second squared. So what is Newton? Newton is kilogram meter per second squared. Is it fundamental? No, it is not fundamental. Again, we have the same quantities. Kilogram is there, mass is there. Length, time. So in the unit of momentum and in force, we have same quantities combined, but in different powers. You can see that power of second is -1 and here it is -2. If we consider joule, what is joule? Joule is the unit of energy, yes. Joule. Is it fundamental? There is only one letter, joule. It is not quite fundamental. How do we represent the units of energy? It is, okay, force times displacement, it is kilogram meter square per second square. Okay, kilogram meter square per second square. Again, the same quantity, length, mass and time, but different units, different powers. So then we have another unit, another quantity, maybe power. What is the unit of power? Yes, that's it. Watt. Unit of power is watt. We represent it by capital W. How do we represent this in terms of fundamental quantities? Again, kilogram meter square second raised to -3, because we divide it again by time. So again, only power differs. Okay. Now we have another quantity. Electric charge. What is the units of electric charge? It is coulomb. C. Okay. Is it fundamental? No, it is not a fundamental quantity, because we have chosen current as the fundamental quantity. So ampere is the fundamental unit. Okay, ampere is the fundamental unit, and the unit of charge coulomb is ampere second. So it's a combination of ampere and second. So it is not a fundamental unit, it's a derived unit. So we have a large number of derived units. You should be familiar with this. So now, by now, you should be able to clearly spot a fundamental unit. If you have a unit, you should be able to identify whether it is a fundamental unit, supplementary unit, or a derived unit. Okay. So fundamental units, there are 7 fundamental units. You have seen that. Supplementary units, we have discussed 2 supplementary units, radian and steradian. And the case of derived units. There are many, we can say there are countless derived units. We can observe any physical quantity and combine these fundamental units. You can take any fundamental unit, any group of fundamental units and combine them in different powers to get derived units. Is that clear? Okay. Now, we have a basic idea about units. Now, we are going to see different system of units. Okay, we are just looking at the background of units. Generally, there are different systems of unit. For example, we are going to see some of them. First of all, CGS system. It's very simple. This CGS system, it depends on the systems are named based on what units they use for fundamental quantities, mass, length and time. Here in CGS system, okay, the unit of length is centimeter. The unit of mass is gram. Okay, and the unit of time, it is seconds. Simple. It's not rocket science. You can simply say CGS, centimeter, gram, seconds. It is CGS system. So you can clearly see that the system is named after what units they use for length, mass and time. Then we have FPS system. Again, FPS. Length, we have foot. Okay, normally I say that my height is maybe 5 feet 11 inches. Then it is an FPS system. So it was it is still used in this FPS system, it is still used. CGS system is used. Now, what does P stand for the unit of mass in FPS system? It is pound, yes. Okay, it's unit of mass, pound. And the unit of time, it is seconds itself. So in CGS system, we have centimeters, gram and seconds as the units. In FPS system, we have foot, pound and again seconds. Then we have the MKS system. MKS system. Length, mass and time. What is the unit of length in MKS system? It is meter itself, that is why M. Unit of mass in MKS system, it is kilogram. Units of time in MKS system, like all the other systems, it is seconds itself. That is MKS system, that is the most widely used set of units. Okay, now we are going to learn about the most important system of units, that is SI system. We can simply say it is the international system of units. So it is the universally internationally accepted system for units to avoid any confusions. So SI system has a particular unit for every quantity that you can think of. So here the quantities that we have seen, the units that we have seen when we studied about fundamental units like length, the unit of length was meter, unit of mass is kilogram, unit of time is seconds, unit of electric current is ampere, the unit of temperature, it is Kelvin, the unit of amount of substance, it is mole, unit of luminous intensity, it is candela. These are all belonging to SI system of units. So that is why we chose the unit of length as mass, not the unit of length as meter, not centimeters, not kilometers, meters, because meter is what the SI system says. Now, then we have unit of mass as kilogram, not gram, not ton, not quintal. It is because SI system, according to SI system, the fundamental unit of mass is kilogram. Then the unit of time that we have chosen in SI system is seconds, not hour, not days, not years. It is seconds. And the unit of current that we have selected in SI system, it is ampere. The units of thermodynamic temperature, or simply temperature, that we have selected in SI system, it is Kelvin. It is not Celsius, it is not Fahrenheit, it is Kelvin, because we have chosen it that way. That is the most convenient way to avoid confusions. So from now onwards, throughout your course, you are going to take the SI system as a reference. Okay, and in many cases it will be convenient to use other units, so it is perfectly okay to use other units as well. But you'll have to keep in mind that we have internationally accepted SI system as the system of units. In many cases, for our convenience, we use a large number of different units as well. For example, to measure the length of this pen, I will not use meters. I'll measure this in centimeters only, because that is convenient. So science, units and all, it is basically for the convenience while learning science. So depending on our convenience, we can choose different units as well. For example, if I want to measure the thickness of this phone over here, I will not use meters, I will not use kilometers, I will use millimeters or centimeters. Suppose I want to specify the size of a microorganism, I'll use micrometers. Or I want to specify the size of an atom, I'll use Armstrong. Okay, we'll discuss about these units later. But always, it is not a hard and fast rule that we should always stick on to SI system. We can always use other units as well, wherever it is convenient. Now, suppose we have these systems. Suppose I want to measure the distance from sun to the next galaxy, or sorry, sun to the next star. It is not convenient to measure it in meters, because the length involved is very large. It is not convenient to measure it using meters. We'll use light years. Or when I said, suppose I want to measure the mass or represent the mass of a bus, I'll represent it in tons. 1 ton is about 1000 kilograms. So it is convenient to use it in tons. So there are a number of other units as well that we use for our convenience. Now, even though we use different units, we always try to relate them to SI units. We always try to specify the relations like this. For example, I have the SI unit of length is mass, right? I want to measure the size of an atom. The size of an atom is of the order of Armstrong. What is Armstrong? It is 10 raised to minus 10 meter. So using these powers, we can represent much smaller as well as much larger quantities. So to represent measurements or to take measurements of much larger or much smaller quantities, we use prefixes. Okay, I'll tell what prefixes. By prefixes, what we mean is, suppose we have a familiar unit of length, centimeters. Centimeter is a very familiar unit of length, because the line segments that we draw in our geometry classes, all they belong to centimeters. You don't take, you'll not be asked to construct a triangle whose side is 10 kilometers. Okay, so it will be centimeters. So what does this centi mean? Okay, it means simply 10 raised to minus 2. So centi means 10 raised to minus 2 meter. So what is 1 centimeter? What does it mean? It means 10 raised to minus 2 meter, or it is 1/100th of a meter. It is as simple as that. 1 centimeter, we are just adding a prefix to meter so that we can clearly state the quantity. Another thing, suppose I want to measure the distance from Trivandrum to Ernakulam. Okay, will we be representing it in meters? It is not that convenient. We'll be representing it in kilometers. Suppose I am representing it as 200 kilometers, say. So here we are familiar with this m. represents meter. We are familiar with the fundamental quantity, fundamental unit meter. What does that K do then? Okay, who's this K? Okay, it is K. What does it mean by K? K means it is 1000 times a meter. So that's a prefix. So we use a large number of prefixes to represent physical quantities in terms of the fundamental quantity. Sorry, fundamental unit. We have there are a large number of prefixes. For example, we have 10 to the power 1. That is what we call as deca. Okay, 10 to the power 1 is deca. That means decameter. Okay, we use the symbol dA over here. So if I use the term decameter, it is 10 to the power 1, that is 10 times meter. Then we have 10 to the power 2, it is known as hecto. Okay, so hectometer represents it is 100 meters. Then we have 10 to the power 3, that is kilo. So what is kilometers? It is 1000 meters. What is kilogram? It is 1000 gram. Then we have 10 to the power 6. What is 10 to the power 6? That is 1 million. 10 to the power 6 is mega. Okay, so if I am saying 1 mega, it means 10 to the power 6 times that fundamental quantity. Then we have 10 to the power 9 giga, 10 to the power 12, 10 to the power 15. Okay, 10 to the power 12 is tera. You'll be familiar with that. 10 to the power 12 it is tera. 10 to the power 15 is peta. 10 to the power 15 it is peta. 10 to the power 12 it is tera. 10 to the power 18 we have 10 to the power 18 is exa. So we have the prefixes to represent much larger quantities. You'll get these entire list of prefixes in your textbook. You'll get it in your notes. Now let's mention some prefixes that are used to represent very small quantities as well. For example, what is 10 raised to minus 1 or 10 raised to minus 1? What is the prefix for that? It is deci. 10 raised to minus 2, that is 1/100th of that. Okay, it is centi, that is centimeters. Centimeters, 1/100th of a meter. Then we have 10 raised to minus 3. You are familiar with this. This is milli. So 1 millimeter means 10 raised to minus 3 meters. That is 1,000. 1 part in 1,000 meter. Okay, then we have 10 raised to minus 6. That is micro. We are represented by the letter mu. You are familiar with this. Micrometer means 10 raised to minus 6 times meter. What does that mean by 10 raised to minus 6 times of a meter? 1 meter divided by this number. Okay, so if we divide 1 meter into 1 million parts, that one part is what we call as 1 micrometer. Is that clear? Now, we have 10 raised to minus 9 nano. That is the term that we use for very small quantities, nano. We have nano electronics. So all these deal with very small ranges, distance ranges. Then we have, you must be familiar with this nano because we talk about the wavelength of light in terms of these nanometers. Then we have 10 raised to minus 12 picometers, oh sorry, pico. Then we have 10 raised to minus 15, that is femto. The size of nucleus is mentioned in terms of 10 raised to minus 15 meters. So like this, we have a variety of prefixes to represent very large as well as very small quantities. We'll modify the SI unit slightly to inculcate these prefixes and represent such quantities. So that is how we make measurement of basic quantities like this. Now, okay, so Till now, let's look at the points that we have discussed. We know what physical quantity is right now. We know what fundamental and derived quantity is. We know what supplementary quantity is. We know what unit is. We know what fundamental unit, supplementary unit, and derived units mean. Then we have seen the different types of units that we use. We have seen different system of units. We have learned about SI system. We have learned how to use different units other than the SI system. We have seen different types of prefixes that are used in SI system to represent the quantities. Okay, you will get the entire list of prefixes, the fundamental quantities, their definitions in your textbook. We are not listing each and every one. Now, we are going to discuss about the measurement of some important fundamental quantities. We are going to discuss about the measurement of length. We are going to discuss about the measurement of mass. We are going to discuss about the measurement of time. Now, we'll begin with the measurement of length. So, length is one of the widely used fundamental quantity. The SI unit of length is meters. We have a variety of units. Now, let's see here what we are going to discuss is how we are going to measure distances. First one, very large distance. Second one, very small distance. Suppose we have to measure the length of, again we are coming to this, we are going to measure the length of this board. What we need is a simple measuring tape. It's a common measuring tape. That's enough to measure the length of this board. Suppose we want to measure the length of a particular river. We'll use other methods to use that. Suppose we want to measure the distance. We want to measure the distance from Earth to the sun. So can we directly do that using a measuring scale or a measuring tape or any measuring device that we have? No, we cannot measure the actual distance between the sun and Earth by actually going to sun. We now know that the sun is at a distance of 150 million kilometers from us. We know that the moon is at a distance of about 3 lakh kilometers from us. We know that the average distance from Earth to Mars is about 40 crore kilometers. If my memory serves me correct, I think it is 40 crore kilometers. So we know all these, but we know the distance to the next star or next galaxy. We know the size of our galaxy. So how do we measure these much large distances? So let's see. For measuring very large distance, we make use of a concept called parallax. We make use of a concept called parallax to measure very large distance. Let's try to understand this concept, this parallax, make sense of this concept. Suppose I take this object over here. Okay, I am looking at this object and on the background I can see the board. So you'll have to pay attention here, please. So I am looking at this object, okay, and on the background I can see the board. So on the background I am making a line. So exactly behind this pen I can see that line. Is that clear? Now by keeping the position of this pen same, okay, keeping the position of the pen same, I am changing my position. So pen was initially over here, okay, pen is initially over here. Now I am observing from another point. So initially I observed from over here, now I am observing from here. So okay, now the background is over here. But if you see this pen, the background will be over here. So you can see that depending on the position of the observer, whether the observer is looking from here or directly in your viewpoint, the backgrounds are different. So if we have a background over here, I'll feel that the object has changed its position. Okay, so there is an apparent shift in position when the observer changes, observer shifts. Okay, you can analyze it using another method. Suppose you can place a pen above you, in front of you. You can look at this pen, okay, by closing one eye, then you will see this pen at one position. If you close your other eye, then the position will shift. Okay, so simply that. Actually, this concept is what we call as parallax, and our eyes make use of this concept to provide us with 3D vision. That is why we need two eyes. For stereoscopic vision, for 3D vision, what we need is two eyes, because actually this difference is what our eyes, what our brain make use of to analyze distance. Okay, we cannot actually have 3D vision with a single eye. We'll need both eyes for that. Anyway, so when we change the position of the observer, the relative position of the object also changes. This concept is what we call as parallax. So let's see how to make use of this concept to measure large distances. Suppose I have a planet. Using a telescope, I have observed a planet. This is the Earth. Okay, this is the Earth and this is a planet at very large distance from the Earth. This is the Earth and this is a planet at very large distance from the Earth. I want to measure this distance of the planet from the Earth. So let's consider two observatories, A and B. We are considering two observatories at different points on the Earth. Okay, the distance between them, let's call it D. Okay, we'll be able to calculate that because both the observatories are on the surface of Earth. We'll be able to easily calculate D. Now, from B to observe this P, we'll have to look at this angle. Okay, from B to look at the planet P, we'll have to look at this angle. So we can measure this angle, right? Yes, we can simply measure this angle. Now again we'll make the same observation from A. If we are observing from A, we'll have to look at this particular line. So the angle is this. Again, that angle can be measured. So we are observing the same planet from B and A, and we are going to measure the visual angle or the angle with D at which we'll have to observe. Now if we know this angle theta 1 and theta 2 using simple geometry, simple angle sum property, we will be able to calculate this theta. Is that clear? So if we are able to find theta 1 and theta 2, we can easily calculate theta. So theta is what we call as the parallactic angle or simply parallax angle. This D over here is what we call as the basis for the parallax. Now let this distance be D. Okay, so this D is very large, theta will be very small, theta will be much less than 1 radian, very small. Now we have theta, we have D. Can we calculate the distance from Earth to that planet? Simple. How can we do that? Using the definition of angle. What is angle? It is arc length. This can be treated as an arc. As long as the angle is very small, this angle is very small, this can be treated as an arc. This, I have actually not drawn this diagram to scale. This angle is very small, much smaller than 1 radian. So using this triangle, we can treat this as an arc. If we treat this as an arc, then the angle is equal to arc length divided by radius. And what is the radius? D. We know the value of theta, we know the value of D. Then what is D? Capital D, it is D divided by theta. So we can easily calculate, not quite easy, but we need the experimental setup and all, but we can calculate the distance of the planet. It doesn't need to be a planet, it can be any celestial object. Distance of the celestial object from the Earth by simply measuring the parallactic angle and the base. Okay, you'll have to keep in mind that we have not gone anywhere closer to that planet. Okay, we are on our home planet, we are on Earth, but sitting on Earth, we can measure this. We can measure much larger distance. So that is one technique of that. Okay. Then suppose We know this. This is the Earth. And this is the planet. Okay, again, I'm not drawing the diagrams to scale. Okay, so this is a planet or a star. Suppose I want to know the diameter of that star. How will I measure the diameter of that star or planet? Using parallax method, I will measure this distance first. So D is already calculated like this. Okay, so distance is already calculated. Now I'll look at two ends of the planet, two diametric ends of the planet, then I'll get this angle theta, or let's call it phi. So if we know the value of D, we know the value of phi, so can we calculate the diameter of this planet? Let it be y. Can we calculate the diameter of the planet or the star? Yes, simply y is equal to arc length is equal to radius into angle. So in these two steps, we can calculate the distance from the Earth to a planet much farther away. And we can even calculate its diameter as well without going anywhere close to that. We do not want to go too much close to the sun or any other stars. Okay. So that's a method to measure very large distances. There are other methods as well. So we have discussed one, and now we are going to see how to measure very small distances. Okay, we are not discussing all the methods possible. Just to give you an idea about how large and small distances are measured, we are taking two examples, so one or two examples. Now, suppose I want to measure the size of this pen or the thickness of a paper. I'll be using our normal measuring devices. We have measuring tapes, we have meter scale, we have normal rulers that you use in geometry, we have vernier calipers. Okay, you'll be studying about vernier calipers. We have screw gauge, and to measure, screw gauge can be used to measure distances up to 0.01 millimeter range. And if the objects are smaller than that, suppose we want to measure the size of a cell, of a plant cell or an animal cell, then we'll use a microscope, optical microscope. What is meant by optical microscope? The microscope which uses light waves to see. We can only see light waves. Anyway, this optical microscope, what they do is they make use of light to see objects of much smaller size. But there is a problem with that. Suppose I want to see an atom or a molecule or a virus. Okay. Nowadays we are hearing a lot about virus. Now suppose I want to see a virus and by a microscope, an optical microscope. Can I see a virus using an optical microscope, or can I see an atom or a molecule using an optical microscope? Okay, let's analyze that question. In optical microscope, what we do is we make use of light. Okay, we make use of light to see objects. What is light? Light is a wave. Light is an electromagnetic wave. We have studied it. And the wavelength of visible light lies in the range of 400 to 700 nanometers. 400 to 700 nanometers. So that poses a problem because the size of virus and size of atoms and all, they are much smaller than that. So can we use light to see objects, see and measure the size of objects whose size is much less than the wavelength of light? No, we cannot. We cannot use the light to see objects of the size of 1 angstrom. It is not possible. Okay, so light cannot be used. Then what will we use? We'll use electrons. You'll shortly learn that electrons, they sometimes behave as waves. Electrons, they behave as waves as well. They have wavelengths, so they can be used to get an image of very small objects. And such a microscope which uses electron beams or electron waves to make an image, to form an image of the objects that we need to see, are what we call as electron microscope. Okay, so we'll use electron microscope, and the size of electron microscope is again depending on the not size of electron microscope, size of objects that can be seen using electron microscope, that depends on the size of electron waves. I am not discussing much about that. So, we have a number of devices that we can use to see smaller objects. Okay. Here what we are going to see is how to measure the size, molecular size of something using indirect methods. We are not directly measuring it using some measuring devices or all. We can use indirect methods to calculate the thickness of molecules. For example, in your NCERT textbook, an example is given of how to measure the molecular thickness of oleic acid. Okay. So, it is done as an indirect way, and oleic acid solution or oleic acid is taken and it is diluted about 400 times. How do we dilute something 400 times? If we take one drop of oleic acid and if we drop it in 20 drops of water, or if we take, to be clear, if I take 1 ml of oleic acid and mix it in 20 ml water, I have diluted it 20 times. We'll do it twice. So, we'll dilute it by 400 times. Then we'll spread this. We'll take a drop of this diluted solution and spread it in the surface of water using some lycosodium powder so that this doesn't dissolve. So, we'll take water, we'll spread some lycosodium powder on top of water, and we'll drop oleic acid solution onto this surface of water. So, due to this lycosodium powder, they will not dissolve. So, what it does is that this oleic acid will form a layer, it will form a film on top of water, it will form a film on top of water. So, we can calculate the area of that film, let the area be A. We will directly measure the area of that film and we will measure the total volume of oleic acid. How will we measure the volume of the oleic acid? Suppose we use 1 drop of oleic acid solution. Okay, we can calculate that 1 drop, volume of 1 drop, that is V. Then what is the volume of oleic acid in this V? It is V by 400. Why is it V by 400? Because we have diluted it 400 times. So, what is the volume of oleic acid? It is V by 400. Okay. What is the area of oleic acid? It is A. Then we can say thickness is equal to volume divided by area. So, here we haven't used any sophisticated measuring instrument like electron microscope or optical microscope. We haven't used any sophisticated measuring instrument. We have used our basic knowledge of science and chemistry to measure the molecular size. Okay, it is just an example. You don't have to think that this is the only way by which we can measure small distance. It's just an example of how we can approximate. It is just an approximation, approximate the size of one molecular or molecular thickness using some indirect methods by not measuring them directly. We cannot measure them directly. Now, suppose we are dropping n drops, then we'll multiply it with n similarly. So we had a basic idea about how to measure large as well as small distances. So if we consider another case, we have seen how to measure very large distance and small distance. Now we are going to see what are the different ranges of length that we will come across in science. Suppose we consider a nucleus. It is not cellular nucleus, it is atomic nucleus. From smaller classes, you must have studied about the structure of atom, basic structure of atom. You know that there is a nucleus at the center of an atom. There are electrons revolving around the nucleus. And you must have learned that the nucleus is very small compared to the atom, very small. But the entire mass is concentrated on the nucleus. If we consider the atom as a sphere of radius 1 kilometers, okay, if we consider a sphere of radius 1 kilometers, then the nucleus will be of the size of, its radius will be 1 centimeter. That is it. Anyway, nucleus is one of the smallest things that we know about, and its size is of the order of 10 raised to minus 15 meters. 10 raised to, its size is of the order of 10 raised to minus 15 meters. And we have seen what 10 raised to minus 15 is called as an SI prefix. What is it called? It is known as femto, yes. So the size of nucleus is femtometers, of the order of femtometers. That means it is close to 1 femtometers. It may be 1 femtometer or 5 femtometer or 4.3 femtometer, like that. This femtometer is also known as Fermi. We affectionately call this as Fermi. So that's another thing. Then the size of atom. Size of atom is of the order of 10 raised to minus 10 meter. What is 10 raised to minus 10 meter? What do we call it? This is what we call as Armstrong. Okay, 10 raised to minus 10 meter is what we call as Armstrong. It is represented like this. Then we have the wavelength of light. What is the wavelength of light? It is of the order of visible light. Wavelength of visible light is of the order of. We know that the wavelength ranges from 400 nanometer to 700 nanometer. So that is one thing. Then we have our normal objects. Its length size can vary from micrometers to centimeters to meters to kilometers. And if we consider the distance from Earth to Moon, it is about 3 lakh kilometers. If we consider the distance from Earth to Sun, it is about 150 million kilometers. So we'll slightly discuss about that. So this is the Earth, sorry, this is the Sun, okay, and this is the Earth. You know that the Earth revolves around the Sun in an elliptical orbit. So elliptical orbits means the distance between Sun and Earth doesn't change, sorry, it doesn't remain a constant, it varies slightly. But the average distance between the Sun and the Earth, average distance between the Sun and the Earth is what we call as the astronomical unit. The average distance between Sun and Earth is what we call as the astronomical unit, and its value is about 1.49 into 10 raised to 11 meters. Okay, 1.49 into 10 raised to 11 meters. That is one unit that we use in measuring the distances in the solar system. Okay, all the distances in solar system, like the distance from Sun to Mars, or distance from Earth to Mars, or distance from Mars to Jupiter, these are all measured not in terms of meter, these are all measured in terms of astronomical unit. Okay, so astronomical unit is a large unit that we use to measure the distances involved in the solar system. Now, the next unit that we consider a slightly larger one is light year. You are all familiar with light year. We know that year is the unit of time, right? Year is the unit of time. But light year is not the unit of time. Light year is unit of distance. What does it mean by this light year? Okay, you know that the fastest entity that we know about is light. Light travels in vacuum with a speed of approximately 3 times 10 raised to 8 meters per second. It is very fast. The speed is way beyond our imagination. Now, this light which travels so fast, it takes only 8 minutes for light to travel from Sun to Earth. To travel this much distance, to travel 1 astronomical units, light takes only 8 minutes. So light year is how much distance will this light travel if it travels with the same speed for a year, for a complete year. If it travels for the same speed of 3 into 10 raised to 8 meter per second, then the distance traveled by light is what we call as 1 light year. So it's very large unit. Light year is very large units. Its actual value is 9.46 times 10 raised to 15 meters. Okay, 9.46 times 10 raised to 15 meters. It's very large unit. So this unit is used to measure the distance between stars, galaxies and all. For example, the distance from sun to next star is about 2.5 light years, or the size of galaxy and all, they are all measured in terms of light year. Now, another unit of length that we use, another large unit of length that we use is parsec. Parsec is another large unit of distance that we use. It is practically the largest unit of distance that we generally use. Practically the largest unit of distance. Its value is about 3.08 times 10 raised to 16 meters. 3.08 into 10 raised to 16 meters. It is very large. It is larger than the light years. It is about 3.24 light years. So it's actually used to measure the distance between galaxies, clusters, superclusters, etc. Now, parsec is, its name is actually parallactic second. Parallactic second, what it means that if we have one astronomical unit, okay, if we have an arc of length 1 astronomical unit and the angle is 1 second, okay, 1 second is 1 by 1 second as an angle is 1 by 3600 times degree. It is 1 arc second we generally use by this representation. Okay, 1 minute is 1 by 60 seconds and 1 second is 1 arc second is 1 by 3600 times degree. So if we consider this arc whose arc length is 1 astronomical unit and this angle is 1 arc second, then this distance is what we parsec. You don't have to learn this definition and all by heart, but you'll have to know that this parsec is very large unit. It is the largest practical unit of distance that we use. It is about 3.25 light years. Once again, it is the distance over which 1 astronomical unit will subtend an angle of 1 arc second. 1 arc second means 1 by 3600 times a degree. So we'll wind it up for this session. So in this topic, in this session, what we have discussed is basically fundamental quantities, their units, system of units, and some method in which we can measure the length between two quantities, how to measure large distances and small distances and all. If you are coming across any doubt, you can contact me. My name is Vineet, and this is my contact number. If you come across any doubt, you can feel free to contact me. Thank you.